excited to share with you this major discovery that's happened in my field. And what I'll do is I'll get started right away, maybe with some motivation. So the key challenge that astronomers face today is that we're sort of stuck on this little speck, right? Or to somewhere over here at the corner of a Milky Way galaxy. And we really don't have much mobility in the sense of moving around in the cosmos. So the only way we can learn about things that are ongoing, let's say out here, is for information to travel all the way to us in some form or another. So up till now, astronomers have been using light to be able to see what's going on out there, and that's served very well for hundreds of years. And many of you know that light is a form of electromagnetic radiation, and it's something that we've been using for hundreds of years, using telescopes of various kinds, including very good ones today. But it turns out that that's actually not the best medium for observation. And there are several issues with light as a tool for astronomy. And what I have here are two main reasons. So the first reason is that electromagnetic waves interact strongly with matter. And what that means roughly is that it's very easy for light to get absorbed by something else or get corrupted, that something gets in the way. So for example, if you've got some dust, some dirt, some gases, and light passes through it, it's going to either get absorbed or it could get corrupted in a way that the information it carries is no longer very interesting. The second challenge that light has is that it's actually not quite produced by the bulk of an astrophysical object. It's produced by the molecules on the surface of the object. So there's lots of information about the outside of an object, but oftentimes doesn't have direct information about what's at the core of an object. For example, it doesn't have much information about the mass of a star, for example. That's very difficult to infer. Or the spin of a star. That's very difficult to infer as well from light. So the idea over here is to use what is called gravitational waves in addition to light. So this is going to be a different way of looking at the universe. And that's what this talk is about. So what I'll do is I'll start out by telling you a little bit about Einstein's general relativity theory, which is really the theory behind gravitational waves. And then we'll get into defining what they actually are and how one does astronomy with them. So keep in mind that this subject, general relativity, is a pretty advanced subject. At the graduate level, students take several semesters to fully appreciate what the subject is about. But I'm going to do it in 5 minutes. So it's going to be a crash course on general relativity in 5 minutes, and then we'll move on with gravitational waves. Okay. So general relativity is Einstein's theory of gravity, which he published in 1915. So it's been more than 100 years. And in this theory, Einstein essentially says is that gravity is not a force in the usual sense. The way to think about gravity is that when you have mass, significant mass, it basically warps the space-time around it. And then if the other mass is nearby, they'll basically be affected by this warped space-time. And that's what we call gravity. So effectively, this gravitational force is really a manifestation of this curvature in space-time, this warping of space-time. It has nothing to do with a push or a pull of one mass upon another. Okay? So to give you guys a bit of an analogy here, what I have is sort of a very simple way to think about this. So imagine you have a flat waterbed, and that's meant to symbolize empty space, okay? And then maybe I can just wait a moment in case people want to. So there's room in the front, in case you don't mind sitting on the floor. There's certainly room in the front. Thank you. I can wait a minute or two so things settle down a bit. Okay, so imagine a flat waterbed, and that's meant to be basically empty space. Now, if you take a heavy bowling ball and you drop it right in the middle of that waterbed, it's going to cause a distortion on the surface, which looks something of that sort, which I'm calling a warped waterbed. Okay. And now imagine you take smaller objects, like let's say a bowling, like maybe a tennis ball or a ping pong ball, and you roll it on the surface of this particular bed. You can expect it to go in a curved path, and particularly to do it just right, you even see it go precisely in a circle. So the analogy one is making over here is that if this heavy bowling ball is like the sun, okay, and what the sun is doing is essentially warping space-time around it in that rough shape, in a funnel-like shape. And the planets that are going around the sun are doing so because they're simply following along this curve in space-time itself. It's not the case that the sun is directly pulling on the planet through a force of gravity. That's sort of an outdated notion. It's the fact that the planets are moving along a bend and curve itself, in space-time itself. So if you think about it like this, then you realize there's something new you can say immediately, and something that Einstein said pretty early on when the theory was first proposed, is that not only would planets move around the sun in this fashion, or matter would move around the sun in that fashion, even if there's a light ray that is sort of passing by, that would also have to bend in the presence of large amounts of matter, simply because light also has to propagate through the same space-time. If space-time is bent, then the light also has to take a bent path, in a sense. And this was the first experimental test done of this idea, of this theory, in 1919 by Eddington, in which he was able to show that if you look at, during an eclipse, if you look at, for example, a star, it's possible to see it even though it's eclipsed by the sun, simply because of the fact that a light ray that's coming from it would get bent by the sun, by the mass of the sun, because of this bending in space-time effect, and actually reach the Earth. And what they found is that this little change, this little movement of the star, apparent movement of the star, is about 1.75 arc seconds. The bending is about 1.75 arc seconds. And that's exactly what Einstein had predicted, that value, many years prior. So this was the first experimental test of Einstein's theory. So what I have here for you, actually, if you're a fan of old movies, I have here sort of from 1923 a little clip from a movie which talks about this for the public. It's quite remarkable, and there's no audio. It's basically just a silent movie. So I'll have you guys take a look at it just for a moment. It's interesting, this comment at the bottom. It says only 12 men in the world would understand this. And they actually try to go ahead and explain this effect through really clunky looking diagrams. Yeah. So 1920s. Anyway, so if anybody's curious, I can absolutely tell you what movie this is, but it's a long movie that actually goes through and explains Einstein's theories, but it's kind of cute that they were trying to do this even back in the 20s. Okay, so going back to where I was. Whoops, I know, I didn't mean to go all the way back. All right, I'll just go forward. Okay, so it turns out that this particular idea that light bends because of mass is something that astronomers use regularly now as a field of gravitational lensing. So the idea essentially is that you can think of large clumps of matter. In this case, you see a cluster of galaxies, and it's effectively acting like a lens, right? You can sort of see it's focusing light coming onto the Earth. So astronomers actually use this technique to look even further out into the universe, in essence, by using known amounts of matter that's sitting in various locations. And they use that effectively as a lens to see further out and infer things, what's going on much further out. It's something pretty neat that's done pretty routinely now. So this effect is no longer sort of untested or anything of that kind. It's just sort of a routine effect that astronomers use. I'm going to show you the key master equation of general relativity. It's actually very simple to explain, even though it looks somewhat complicated. So on the left-hand side, that's called the Einstein tensor, and it's supposed to give you a measure of the curvature of space-time. So it gives you a quantitative measure of how space-time is curved. On the right-hand side is something called the energy momentum tensor, so the analog of the stress energy tensor, which many of you may, in engineering, may be familiar with. And that gives you a sense of how matter is distributed in the universe. So effectively what this equation is saying is that the presence of matter, okay, causes space-time to bend. And if you've got bent space-time, that causes matter to move in a different way. And so essentially, gravity is more of a dance between geometry of space-time and matter. And that's really the key piece to Einstein's theory. So because of this sort of poetic way you can think about Einstein's theory, oftentimes is referred to as the most beautiful theory ever written down, and I absolutely wouldn't deny that, ever, that it is absolutely remarkably simple and beautiful. Okay, so that was my crash course on GR, on general relativity. So let's move on. So that was something that Einstein did in 1915, more than 100 years ago. So a few months later, he started looking at the equation and started trying to find solutions to that equation, which basically means applying the theory to looking to natural phenomena. Okay? And he found that in 1916, a few months later, he found that if he did a perturbative type expansion, there were actually wave-like solutions in this particular theory, and these waves travel at the speed of light. Okay. So here are the first two papers published on gravitational waves by Einstein. This was 1916, if anybody can read that date. And if you kind of squint your eyes, you may see that he's doing something like a perturbative expansion over here. Those of you who know roughly what that would be in the context of GR. And here's a 1918 paper, and of course the term gravitational wave is starting to be used at this point on. Okay. So, but to give you guys a sense of what it actually means from a more physical perspective, when I mean perturbation, that roughly means a disturbance. And what one is saying is these are disturbances in space-time itself, and they happen to travel at the speed of light according to the theory. So oftentimes they're referred to as ripples in the fabric of space-time, and that's sort of a fairly accurate way to think about them. If you imagine you have a surface of a pond, you disturb the surface of the pond, you have these ripples that form and they travel outward at a pretty fixed speed. In the same sense, if you disturb space-time somehow, you have these ripples that form that travel the speed of light, and these are really what gravitational waves are. So, of course, you're going to want to know what do you mean by disturbing space-time. So it turns out you disturb space-time every time you accelerate mass. So even when you, for example, step on the gas in your car, you accelerate your car, which is a fair amount of mass, you produce a gravitational wave. Of course, it's so tiny that it has no impact, but that's how you would make a gravitational wave. Anytime a mass accelerates, produces this little ripple in space-time. And much like light, they carry away energy, momentum, and angular momentum from the system that they're being generated from. Okay. Fine, if anybody has a question anytime, just sort of, raise your hand, and I'll be happy to answer. So coming back to the question I originally asked, which is why use gravitational waves to do astronomy? Why not just keep using light? So three reasons. So the first reason is the fact that gravitational waves actually are produced by the bulk properties of the system. So effectively, gravitational waves can directly tell you what a system's mass is, spin is, size is, and so on and so forth. So they'll give you bulk information, which, like I said earlier, is difficult to extract from light-based astronomy. The second thing, which is perhaps even more important, is the fact that these waves are almost impossible to slow down or stop or absorb. They can go through miles of lead and not be affected. They can go through a whole star and not be affected. These things can travel for billions of light years and completely be unaffected. So that makes them invaluable as a tool for astronomy, because that's what you really want. You don't want something that gets corrupted on the way, and these would absolutely be impossible to disrupt and disturb. And the reason for that is because gravitational waves interact weakly with matter, and something that I'll point out a little bit later too, because that's important. And the last thing let me point out over here is that it turns out that for most common sources, which I'm going to get into next, turns out that the frequencies of these waves happen to be in our audio band. And they're vibrations in the audio band. So oftentimes we refer to them as sound. They're not really sound, but they're like sound. And not that something that we could hear, because they're very, very weak, like I said. But oftentimes this is referred to as being able to listen to the universe, in addition to being able to see it through light. So in a sense, what I'm saying is we're opening up a completely new sensory organ onto the universe. Okay, so some strong sources, some examples of strong sources of gravitational waves. So the strongest sources happen to be those that are dense objects, very massive objects that have very high accelerations. And good examples of those are supernovae, which my colleague Bob Fisher is an expert on. Do I see Bob anywhere? Oh, hi Bob, right. So he's an international expert on this, on these type of events. And then, of course, collisions of compact objects like black holes, which is something that I work on. So what you have here is essentially two black holes that are giving off these waves that are shown in little ripples as they come close together. Okay, so I have a little video here that I can show you that shows you the collision of two black holes. All right. All right, so what you're seeing here essentially are two black holes that are orbiting each other. We'll zoom in and see that in a moment. And what you're seeing in orange or red here is what these gravitational waves that are being released by the system. So these two black holes get closer and closer together because they're losing energy because of these waves that are leaving the system. And as they get closer, the waves get more intense, and you'll get to see a big burst of them right before the black holes coalesce and merge into a single one. Right, so that's kind of the idea that we're talking about here. Okay, so now how do we know these waves actually exist? Okay, so it turns out that since the 70s, we've sort of known indirectly that they actually exist in this particular manner. So two astronomers, Hulse and Taylor, that happen to be at UMass Amherst. So the UMass system certainly has some history, in this particular field. We're observing this binary neutron star. So you've got two neutron stars that are orbiting each other. And what they found is that over time, these two neutron stars were getting closer to each other. So essentially, they were in-spiraling into each other. And they noticed that because the orbital period was actually decreasing. So they were getting faster and faster as they were in-spiraling. So it wasn't clear why, because the system is fairly isolated. There isn't any interference from anything else. So what they sort of assumed is that perhaps gravitational waves are leaving the system, not something that they could actually see. And that's causing a loss of energy, and therefore the system is beginning to spiral into each other. So what they did was they calculated using general relativity what the in-spiral rate would be, and they found that it would be somewhere on the order of 3 millimeters per orbit. And based on that, they were able to calculate how the orbital period would actually change. And if you basically graph their data, so this is the raw data, and by the way, there are error bars. They're just so tiny that you can barely see them. So very precise measurement that they were able to do with this. And if you graph the prediction from general relativity, this is what it looks like. Okay. So it's remarkable because keep in mind that this GR prediction that I'm talking about didn't require any tuning. This is literally raw data plotted together. There was no parameter that was tuned to make it look pretty or anything of that sort. So this was the first very strong evidence that these waves are absolutely genuinely there. We just haven't been able to see them directly. And here they're very happy because they've just been given the Nobel Prize in the 90s for this discovery. Okay. So this was the clearest indirect proof that we have that these waves actually exist. Okay, so the question is, why haven't we seen them? This was the 90s, it's been 30 years. Why haven't we actually gone ahead and directly measured them until, of course, the last few months, as I'm sure you all know, which is why you're here. So the reason is, going back to that statement I made earlier, that gravitational waves interact very weakly with matter. If they interact weakly with matter, that's a good thing for astronomy, because they can pass through anything. But there's also a bad thing, because the only way we would measure them would be by interacting with them using matter. So if they interact weakly with matter, we're going to have a rough time detecting them, in essence. That's the other side of the coin. So here's an example of that. So imagine you have the collision of two solar mass black holes occurring at a typical distance, let's say 100 megaparsecs away. And it turns out that that particular gravitational wave, which would be fairly strong, by the time it comes to Earth, would basically cause a change, would cause a strain of 10 to the negative 21 meters. 10 to the negative 21. So what that means roughly is that if you take two masses and you place them about a meter apart, so somewhere around this distance over here, this wave would cause them to move or wiggle relative to each other by 10 to the negative 21 meters. That's the small amount of distance that you actually have to measure. So what is that? That size is about the millionth the size of a proton, in essence, what we're talking about. So tiny, tiny, tiny distance these masses are going to move. So how do you go ahead and do that? Yeah. Mm-hmm.
So if the gravitational waves interact so little with matter, or they affect them so little, how does the actual, how do they get the information from the matter they interacted with?
Right, so that's what I'm going to get into next.
Oh,
right?
Sorry.
Great, no problem. So how do you do this? And of course now you all know this has been done in the last few months, and this is what the whole announcement was 2 weeks ago. So how does one go ahead and do this? So there are 6 detectors currently that are in the works at some stage or another that do this. So The two largest ones are in the US, LIGO, Hanford, and Livingston. This is the largest project ever supported by the NSF. It's touching $1 billion, large undertaking taken by the NSF. Then there are two detectors in Europe. So GEO is a small detector which was built in collaboration of Germany and UK. Virgo is a detector that's comparable to the size of LIGO and is currently down for upgrades, but it's going to be back online later this year. And it's something that is a joint collaboration between Italy and France. And then there's Kagra, that's a Japanese detector that is going to come online maybe in a few years. And it's being built deep in a mine underground. And I'll talk about why that's important. And then finally, just last week, unsurprisingly, India also went ahead and agreed to a detector in India, which is being built jointly in collaboration with LIGO. So already we have 6 detectors that soon are going to be in operation. There's 3 already in operation. So let's talk about how they actually work. So all of them have the same exact principle of operation. So imagine you take a number of free masses, okay, and you arrange, and let's think of just being in vacuum and empty space out there, and you arrange them in a ring. So free masses arranged in a ring, they're not interacting with each other or anything of that sort. So they would just stay there in a ring form forever, right? Now imagine if you have a gravitational wave that goes right in through that particular ring, it would cause a distortion of that type. It would basically cause a compression in one dimension, extension in the other, and that cycle would keep going through in that particular way. But keep in mind what I'm showing you is highly exaggerated because that strain, the change in length, so even if this ring was, let's say, a meter big or something, the change in length, the movement would be of that scale. So you'd never be able to see it, certainly not like that, right? So, however, if you built the ring to be really big, that scales up, okay? So imagine you build this ring to be, let's say, 4 kilometers big, then you have to only measure 10 to the negative 18 meters, which is 1,000th the size of a proton. Big improvement from 1,000,000th the size of a proton, right? It's an improvement. Okay? And that's what LIGO actually does. That's the distance scale it actually measures. So how do they do that? So you don't quite build a ring that's that big. So what you do is you say, okay, we'll pick 2 points of that ring, which is going to be the top and the left. And that's going to basically be the 2 things we're going to watch. We're going to see how much they move. Okay? And they're actually mirrors. They are several tens of kilograms in size. You'll see pictures in a moment. And what you do to measure if they're moving or not is to bounce lasers between them. Keep in mind they're 4-kilometer long arms now, okay, because you want to have that scale. Okay. And you use interferometry to see if you actually have a movement at the end of those 2 mirrors. And I'll explain in a moment how that works. And that's effectively what the setup is, very straightforward. So I have a little video I can show you that explains this really well. And it's something that the collaboration developed for this purpose. So essentially what you're seeing here is the source of the laser, a beam splitter, and you'll see in just a moment how the waves work. So, so imagine you've got this laser, high power laser coming through, it splits into 2, and the setup is designed in a way that once the mirrors reflect back, the 2 lasers that come back interfere in a way that they cancel each other out, and you see absolutely no signal, no light at all on the screen. Now, if a gravitational wave goes by, these mirrors are going to start to move, even a little bit. That's going to cause a change in the interference pattern, and that's going to end up meaning you get to see some light on the screen. So it's a very, very simple setup. It's a standard Michelson interferometer. Physics 100 level, 200 level physics classes talk about this. Very, very simple setup to go in and detect this kind of movement. But the only key thing is this is basically going to be a movement that's very tiny, and it's going to be a scale that's basically kilometers big, right? Give you guys a sense of how small is this particular distance to the negative 18 meters. Okay, so 1 meter is about 40 inches, so it's roughly around this size. You know, everybody has a sense of what a meter is. Chop that into 10,000 pieces, and you end up getting the thickness of a human hair, and that's roughly 100 microns. A micron is a 10 to the negative 6, a millionth of a meter. Okay. So you take the thickness of the human hair and you chop that into 100 pieces, and you get something which is the wavelength, roughly the wavelength of light, which is about 1 micron. You drop that by another 10,000, you end up getting the size of an atom, which is about 1 angstrom or 10 to the negative 10 meters. That's the size of a hydrogen atom, for example. And you drop that by another 100,000, and now you're down to the size of a nucleus, which is 10 to the negative 15 meters, or about 1 femtometer. Okay, the units could go with that. LIGO sensitivity is 1,000th of that. Okay, so you have this mirror, which is tens of kilograms big, and it's about 1/3 of a meter wide. So essentially this huge thing, which moves by that much distance. So for those of you who know physics would basically realize this is quantum mechanical movement that's being observed for a macroscopic object, for a big heavy thing in essence, right? So it's quite remarkable that one does this. So this is the most precise measuring device known to man that has been built, to date. Okay. This is quite remarkable. So a bit more about the project. So there's 2 detectors, one in Livingston, Louisiana, one in Hanford, Washington. It's a joint project that was put together by Caltech and MIT, that's led by Caltech and MIT. But there were 100 other institutions that participate in it directly, and there's several other institutions and people who contribute to other collaborations, and we're certainly one of them. And this was, like I said, the largest project ever funded by the NSF. So here's a picture of the Livingston Detector. You can sort of see the 4-kilometer long arms. So one goes this way, one this way over here. Here's the Hanford site, which is sort of desert land that was donated by the Department of Energy. And that has fewer incidents. There's nobody there, and it's a desert. So not as interesting, but it's the exact same setup. You see 4-kilometer long arms, and it's identical in every way. So a few pictures here about the lasers and the vacuum. I know nothing about this. I'm not an experimentalist, but I thought I would show you. That looks fancy and pretty. Here's what the suspension system looks like, and this is actually the key to the success of the project, because remember that one of the major sources of noise, which I think maybe Chung pointed out, would have to be vibrations from the ground, seismic noise in essence. That's a major issue, which I'll speak of later too. So it's an active seismic isolator. Essentially what it does, it measures the ground motion and it subtracts it out dynamically. So this is a very sophisticated part of the setup, and again I'll talk about it in a little bit. Here's the control room. And again, even all this looks fancy. The bottom line is this is the most precise ruler that's ever been built. It's just measuring distance. Okay, so let's talk about the noise a little bit, because there have been a couple of questions on that. So here's what you see are essentially all the different noise sources, the important ones, that are all plotted together. And in black, you see the sum total of them. So this is the actual total noise level in the detector. This is for the current version of LIGO, the advanced LIGO it's called. And you can see the scale of it is roughly right. 10 to the negative 21, 22, here's where the detector would operate. The scale is roughly right. The noise levels are below that. So what I want you to in particular notice is this, at the low frequencies, there's a very sharp increase in noise here. So this one is a limiting noise, the one in brown, at very low frequencies. And what that is seismic vibrations. It's very hard to isolate the movement of the ground when you get to low frequencies. That's a very sharp increase. So this basically tells you is that in the future, if you want to basically look at gravitational waves at lower frequencies, let's say in this region, you can't have it on the ground. So either you got to go deep in the ground, which means, let's say in a mine, and this is why Khanna is being built underground, where seismic noise dissipates, or you got to build it in space. And that's going to basically be the next place where the next generation detectors will go. They will have to go in space, because this noise would completely be absent there. There are also other many sources of noise that I can talk about, but I'll just leave it at that right now. Just keep in mind that seismic noise is a really severely limiting issue for low frequencies. Okay, so here's sort of a quick slide that shows you what the range of LIGO is. It's not the best looking slide, but it just tells you. So this was the original LIGO detector that maybe from a decade ago, which could see a fraction, maybe a few tens of millions of light years. This is the current generation one that can go a little bit further out than giga light year, so about a billion light years away. And a huge part of the sky, of course, is visible to the detector. So I'm going to move from one topic that is not my expertise, the experimental part, to another topic that's not my expertise, which is the data analysis part. But this is going to be interesting to some of you, so I think it's worth talking about. So data analysis in LIGO is a very interesting thing. So partly the reason is that it was always expected that even the strongest gravitational wave signals would barely be above the noise. As you saw, the noise is a big issue. There are lots of sources of it. So the expectation is that the noise level is going to still be quite high, and what engineers like to essentially say is that the signal to noise ratio is going to be very low in the kind of data one gets. So how does one go ahead and work with that limitation? So once again, in electrical engineers in particular, I know John is here, who's all the way in the back, right? So he teaches a class in which he's going to use this as an example now, right? This is standard technique being used by, let's say, graduate level students in electrical engineering of the notion of a matched filter. So you could essentially have low SNR, but you can do something called matched filtering that can help a lot. And what's the idea there? The idea is if you have a sense of what the noise distribution is like, if you can model the noise in some way, you can also have a good sense of what the signal looks like, a fairly precise sense of what the signal looks like, the real physical signal. You can use this information to remove the noise, to factor out the noise. In other words, that can help you pull the signal out of the noise and increase the signal-to-noise ratio. Okay, so the idea is that, but in this case, you can imagine this is fairly challenging because, of course, you can have a sense of what the noise is like. That's mostly going to be coming from measurement. But what do you know what the real signal is going to look like? How do you know what to expect to see? That's what you were hoping to be able to get from nature. So we need to come up with the answer, the real physical signal beforehand. And that's something that the community refers to as a template signal or a template waveform. And that must come from somewhere else. Okay. And then once you have different templates, you have to look for each and every such template in the noisy data stream. So there's a lot of challenges in data analysis over here. It's a unique kind of data analysis. So the first question is, how do you come up with the answer first? How do you come up with what to expect to see? What would LIGO actually see? So the answer to that is that we bet on Einstein. Okay, and Einstein has a good reputation, right? So what we do is we basically imagine that general relativity is a valid theory and it's going to work everywhere in essence. And then we use that as a way to model the sources, for example, black hole collisions or whatever you have. And then you compute the signal based on what the theory says, and you use that as your physical signal. Okay. So the model certainly needs to be pretty accurate for this to work correctly, and this is the place where my group contributes. And I'll tell you guys a little bit more what I do in a moment, but this is the place where the theorists contribute. And it's an important contribution because if the theorists screw up, if they get it wrong in essence, then basically even if the signal is there, it'll never be found, because it may be deep in the noise and the filtering wouldn't help at all in that situation. So it's pretty high stakes for theory as well in this situation for a successful detection. Okay, let's say a few things of what I do in that context. So we basically contribute to the source modeling effort. This is all NSF supported work, obviously. And a specialization that I have in my group is situations in which sources in which one of the black holes is much larger than the other. And it requires fairly sophisticated mathematical and computational modeling techniques. Okay. And I should point out that the Center for Scientific Computing on our campus is pretty key to success with regard to these type of things, and not only just because of our novel supercomputing resources, but also because of the strength of students and faculty, both in the math and physics department, that have all contributed in various ways. Okay. So here's an example of what the signal would look like from theory, okay, from general relativity. And this is from two black holes merging together and forming a black hole. And so what you see are three distinct phases. So you sort of see right at the beginning, there's a low frequency, what we call chirp, sort of a higher amplitude, and you have a low frequency that's to start out. This is the in-spiral phase. So the two black holes are far away, slowly sort of spiraling into each other. And they're getting closer, which is why the signal is going up in strength because of the emission of gravitational waves. And the very end over here is called the ring down phase, which is once the two black holes have formed a single black hole, they've merged together, and now they're just simply, the system is just simply settling down to its final state, and that's the ring down phase. And in between the two, you actually have something called the plunge or the merger phase, which is the part, which is the complicated part when the merger actually occurs, and the settlement beyond that, settling beyond that begins. Okay. So I want to quickly just recognize my two students who are here. So Sarah, would you stand up quickly? So Sarah's working on the transition of the merger to the ring down. Okay? And Isaac, could you stand up please? And he's actually looking at the possibility of another phase. So it turns out that once this signal dissipates, there's another signal that shows up, which is called the tails, which is called the tail signal, and that's another phase that could be interesting, and that's what Zach is looking at. Thank you, guys. So clearly, what I pointed out from an analysis perspective is fairly computationally challenging, because not only do you have to come up with templates modeled from theory, and then you have to look for each and every single template in the data stream. So to give you a sense of how many templates there are, so typically one uses 100,000 to maybe 1,000,000 templates. So you have to look at all possible sources, and you look at about 1,000,000 representative sources, black holes with different spins, different masses, and you try to solve for this type of signal from those. Then you look for each and every single one in the data. So it's highly, highly computationally intensive. And it's worth pointing out that the center resources contribute to this effort, both of them, in the sense of source modeling and also in the sense of looking for the signals in the data, okay, including the PlayStations. I had to have a picture of them in here, right? Okay, so I can finally get into what happened 2 weeks ago, or what was released 2 weeks ago. So 2 weeks ago, the LIGO team sort of ultimately unveiled the fact that they have seen the first ever detection of a gravitational wave. That's the signal they actually saw. So this is the signal in the Hanford site. That's the signal in the Louisiana site. And you can sort of see it looks very much like what I showed you earlier. In the sense you see the same kind of in-spiral phase. You see something like a plunge or a merger phase, and you see a ring down phase of some sort. Okay. And this event actually occurred on September 14th. Which is why it's being labeled as the date over there, gravitational wave, September 14th, 2015. And it turns out that this was soon, just a few weeks after the detector had just finished and had reached the stage of what they call advanced LIGO, which was a 5-year upgrade cycle. So they'd spent 5 years upgrading the detectors, getting the noise levels down to much lower sensitivity, and they literally had turned them on, and they basically got to see this event, which was very fortunate. Okay. So here's what the signal looks like once you clean it up using match filtering. So now you believe it, right? So this is basically the gray signal is what you get when you do the match filtering that I talked about. And overlapping with it in red is the theoretical signal based on computation that is the closest template, so to speak. So you can see they overlap, beautifully together, right? And so it's clear that this particular signal is coming from two black holes merging together. And based on the template one uses, here you can figure out the masses and spins of these black holes and other details that I'll talk about in a moment. Okay. So here are some details. So this is a signal coming from a binary black hole system. The two black holes happen to have solar masses, have masses of 36 solar masses and 29 solar masses. And the final hole happens to be about 62 solar masses. Remember I pointed out that you can get information about masses and spins really easily, and you can see immediately that's what they actually get, pretty much right off the bat looking at the signal itself. One can also tell that the system was located 1.3 billion light years away, which means that this collision happened over 1 billion years ago. So it's almost chilling to think about it in this particular way, which is, so you have these two black holes 1 billion years ago, they come together and they merge. And a signal is released, a strong signal is released from there, is traveling its way to us for 1 billion years. It travels all the way to us. When the signal actually formed, meaning when the black holes merged together, human beings of course didn't exist. Life was just getting started on Earth, right? And evolution carries us all the way to the point that we build this detector, right? And we turn it on, and the signal passes right by, and we catch it. Right? It's quite a remarkable thing. Right? It's almost chilling to think of it in those terms.
Gaurav?
Yes.
If this gravitational wave actually is passing through, let's say, another black hole, can they get out of it? I mean,
No. So if it basically goes, it would scatter, and some of it is going to scatter around it, and some of it would go in, and what's gone in, it can't, of course, come out. Absolutely not. Yes.
So even that wave cannot get out of that.
Absolutely. Yeah. So it's quite chilling to think of it in those terms, but it's something that, with a fair degree, and again, for those of you who like some statistics, essentially, if you want to compare what was seen to pure noise, then the likelihood of that is basically really tiny. So there's a huge amount of confidence that this is what was seen was really a true signal.
Gaurav, is that confidence based on one detector or the joint?
Joint. Okay, so one thing also I want to quick point out is that...
So Gaurav, given the fact that this was detected immediately after the sensitivity was increased, and this happens billions of years ago, is it fair to assume that so many of this had happened in the past and we're likely to see them every other day?
Absolutely. So the event rate are hugely uncertain, but the expectation certainly there will be several events every year that one would see. Of course, there have been many events like this that we just didn't have the technology to be able to see, and this is the first one in essence, yes.
Professor,
Yeah.
we see after the merge, 3 solar masses lost. So this mass loss is due to the emergence of the gravitational waves and another form of energy.
Right, so I'm just going to make a comment on that. So just hold on one thought. BK, yes?
Yes, speed of light and speed of waves, are they different?
Exactly the same. Yeah. Okay, so just pointing out what Tazkira said, which is if you take a sum of these two, you get 65. You subtract out 62, that seems like some mass has been lost in the collision, and that's absolutely true. So there is energy loss that's occurred, which has gone largely into gravitational wave radiation. So you have 3 solar masses worth of energy that these waves were released in. And to give you guys a sense of what that power is, so remember, I'll go back a little bit and just remind you guys of the time frame. So this time frame is a fraction of a second, right? So essentially what one is saying is that you have so much energy that was released in a fraction of a second, 3 solar masses worth. So the power you get is about nearly 10 to the 50 watts from that particular collision, which is far more than gamma ray bursts, which is several orders of magnitude lower gamma ray bursts. This is a really, really huge amount of power. And to give you guys a sense of scale there again, so this is 10 times more power output than taking all the number of stars and galaxies combined, their electromagnetic output, meaning their light output, combine them all together. This is still way higher than that by a factor of 10. So a huge amount of energy radiated by this black hole, by a single black hole collision. So here's a quick video that shows you guys the collision if you were close up front. So if you could see the collision happen close by, that's what it would look like. Here are the 2 black holes in orbit. You can see they're roughly the same size. One is slightly smaller than the other. The reason why the stars are dancing about, of course, is because of lensing, gravitational lensing that I pointed out earlier. And you'll just see the whole thing happen very quickly and very nicely and quietly, but keep in mind that there are 3 solar masses worth of energy being released by this whole thing, and you ultimately settle down into a single black hole that's much bigger. That's it, right? Just a fraction of a second and it's all over, but a tremendous amount of energy comes through. Okay, so here's the paper. Okay, so here's the paper. If anybody wants to read it, it's very well written. This is sort of the citation of it. And the expectation is that the 3 lead scientists, Caltech and MIT, essentially, who led the project, will be getting a Nobel this year or the next. This year may be too late. The nominations have already passed, so it may be too late unless the Nobel Committee does something special. But certainly, if not this year, it'll be next year. Okay. So I want to say a few words about the significance of this. Most, sort of media has been talking about the significance because it's the first direct detection of gravitational waves, and that's certainly very important. But I want to say a few other things too. So first of all, this is the 100% conclusive proof that black holes exist. The reason is because this signal could not have come from anything else. In particular, that ring down phase, the phase in which the black hole settles down after it's sort of merged together in a single black hole's form, it's called quasi-normal ringing, okay? And that can only come from a black hole horizon. It cannot come from anything else in nature. So that's clear evidence black holes exist. Moreover, it's clear evidence that binary systems do exist and black hole binary systems exist and they merge and so on and so forth, exactly as we would predict. The second interesting point I want to make here is that this is one of the very few strong field tests of general relativity. So general relativity has been around for 100 years. It's been tested many times over, and it's always passed every single test. But most of the tests have been on Earth or have been in the solar system. And both on Earth and solar system, gravity is fairly weak. So GR has only been tested in what's called weak field, when gravity is fairly weak. And space-time isn't really that distorted. But this is a test that happens really in the strongest field you can imagine of two black holes merging together. So, so the fact that general relativity agrees so well with what was observed is really a huge thing to pay attention to, simply because there hasn't been many, if any, strong field tests like this in the past. Of course, I should point out that the fact that the entire LIGO project, the entire pipeline works from the measurement to the theory to the data analysis, given how involved it is, that's a huge success on its own. And this is truly the birth of this thing called gravitational astronomy, which this talk is about. Okay, so in short, I could just say that the significance of this is that Einstein was right again. It's worth pointing out, though, that he did not believe in black holes. He thought they were too weird to be true, and he also didn't think we would ever measure gravitational waves. So was he really right? Well, maybe not personally, but his theory certainly was absolutely right. No question about that. We'll give that to him. All right, so a quick slide on the future. So essentially, I want to point out that this is just the beginning of the field, and we expect advanced LIGO will make many, many more measurements this year and in the following years. And keep in mind that there are plans to upgrade it. In fact, it's down again for many months for another set of upgrades, and it's going to come back online in August. So, and it's going to emerge as overall 10 times more sensitive than it was a few years ago. Virgo will come online later this year in 2016, and then these two detectors, one in Japan and one in India, also maybe in the early, another couple of years, less than a decade, we expect to have them online as well. So there'll be 6 detectors that will be looking for the same sort of thing. And so in the future, hopefully before I retire, there's going to be the space-based mission, which is called LISA mission. It has a detailed plan. It was supposed to launch this year, by the way. This has been delayed to 2034. So this is basically 3 spacecrafts that are basically going to be millions of miles away from each other, and they're going to follow the Earth around the sun. So it's a huge instrument that is going to follow the Earth around the sun. And it's the same principle, interferometry. So laser is going to bounce back and forth, and this will be a very sensitive, an ideal tool to do detailed gravitational astronomy. I'm going to stop here and leave you guys with this slide, which basically shows you the entire gravitational wave spectrum, which is very much like the electromagnetic spectrum. The different sources that would produce waves of different frequencies, and of course the different detectors that currently exist are going to be planned or going to be built that would eventually be able to see this radiation. And this is really the beginning of this new field of gravitational astronomy. Right, thank you so much.